Hi class, good day to you. Welcome to the first lecture on quantum field theory, and this is for this semester. And we're going to start with the preliminaries of this lecture. Of course, this is very important as well as in the coming chapters of this particular course. So I'll just take out my video cam so that we would concentrate more on the notes. So we start with the units convention. So our reduced Planck's constant and the speed of light would just be equal to 1. And so in this system, the length would be equal to the time, equal to the reciprocal of energy and the reciprocal of mass. So in that case, your quantities like the mass, the rest energy, and the Compton wavelength would just be the same, equal. So you have m equal to mc square mc over h bar. And then, so as an example, you have the mass of the electron equal to 9.109 times 10 to the 28 grams would be equal to 0.511 MeV equal to 3.862 times 10 to the negative 11 cm to the negative 1. So part of the convention would be that the metric will be using the metric most of the time, but of course you will get used to it later on. So here's the metric called the Minkowski metric, which is the simplest of all metric, where the components is only non-zero in the diagonal. So you have the first component, which is of course associated with the time. So you have 1, and then for the other 3 diagonals associated with space is negative 1. So you have a metric that has indices mu nu under and mu nu above. They are just they are the same, but they can be used on different situations. So you can use the g mu nu below, the indices below, and g mu nu which are written also above the g. And if you can see Greek indices, then they would tell you, it would tell you that it runs from 0, 1, 2, and 3. So there are 4 components. So the 0 would signify the time component, and 1, 2, 3 would be the spatial component. And if you see indices ij, or the English alphabet indices, they would just denote spatial components. That means it runs from 1 to then 3. And if you see repeated indices, that would mean summed indices. So say for example you have this. So say for example you have G mu sigma, G sigma nu. This means this is sum. So you have G mu 0, G 0 nu plus G mu 1, G 1 nu plus G nu 2 g 2 mu plus g mu 3 g 3 mu. So that's just the meaning of the repeated index. You have to sum the four components. So also when you see a character, that usually means a constant or a 4 vector. So here this is just a 4 vector, so v. And if you have a v with an arrow above, that is just a 3 vector, means that it's a vector with components of space. This one has components of time. And you also have this one here. This is also a 4 vector. This is the formal representation of a 4 vector. You have x mu with an index above. That means x0, then you have x 3 vector component, or xyz for example. And if you put the index down, that would be that would change to negative x. The space part would change to negative s. But by the way, if it starts with a negative here, then if you change the placement of the index, whether up or down, it becomes negative here. So that's just it. Again, the formal 4 vector notation would be, there is an index either up or down of the character, and so this one is a 4 vector, and this is also a 4 vector with an index that is below, written below, and that would just have the opposite sign of the original 4 vector with the upper index, and the opposite sign of the spatial components, I mean. So how is this being done? So if you have an x mu, say mu would be this one, x mu would be this one, x0 x negative y negative z, for example. This would be x mu would be j mu, or say mu nu x nu. So this one, this mu here is the result of the contraction of nu and nu, the upper nu and the lower nu. You can only contract an upper and a lower. Both upper does not contract. So, but anyway, there are some, no? So as I've said, this would be equal to g mu 1 x z mu 0 x0 plus g mu 1 or x 0 plus x g mu 2, sorry, this is 1, x2, and then plus g mu 3 x3. Now for x0, this would just be g mu 0 0 x0. The rest would be, this would be 0, for this would also be 0, and this would be 0, so there's nothing you can add there. So your x1 would be g1, the g10 would be 0, so you don't include that. So this is just g11 x1, and x2 would be g22 x2, and then x3 equals g33 x3. That's just what it means. So in this case, you will have x mu equal to this one is this is of course equal to, this is 1, so this is 1 times x sub 0, so that will just be equal to x0 this is x0 because it will contract to, this one will carry the index below, so this will now be 0, and this one is just, this is -1, and so you will have this one to be negative x1, and this is equal to negative x2, and then this one is negative x3, but in this case you have x1 equals x, so this is now your x mu below would be equal to x0, and then you have negative x, opposite sign of here, y and z. So that's just your x mu compared to your x mu, which is x0 x negative y negative z. So that's just it. So you will also have a scalar product of, say for example, a quantity p and x. In this case, we usually write we usually denote the momentum to be p and your x as a 4 vector space-time. And so this one px is just, when you contract the mu here and the mu here, they will eliminate the index, and the nu here below and the nu below. So this will just be equal to px, p sub p of o and x of o, or x to the o, minus p dot x, the p vector and the x vector. And for massive particles, your square of momentum would be equal to e squared minus p squared equals m squared. That's just the energy equation. So in this case, this is equal to the energy equal to momentum square plus mass square. So for derivatives, this is quite tricky because your partial derivative or partial mu is equal to partial with respect to x mu, where mu is an upper index, and this is just equal to partial x0 del operator. So when you have when you see this is just equal to 1. Well, of course, the index here will contract. The mu and the mu here will contract. And if later on we will also encounter this epsilon, mu, nu, rho, sigma. This is just an antisymmetric tensor, and this antisymmetric tensor is when you have 0, 1, 2, 3 here as your index above, this is positive 1, but if it goes down and this cycle goes down, it becomes negative 1. And when the cycle is this, if you this one, if you put the 0 back at the back of the 3, that's another cycle. It becomes a negative 1. This is, by the way, the Jackson convention of this antisymmetric tensor. And if you see indices repeating, at least 2 indices repeating, that would be equal to 0. For quantum mechanics, E is equal to I. This is I is negative 1 here. Partial x0, and the momentum is just negative I times the del. So if you combine the two in quantum mechanics, you have the form momentum here. Form momentum of a particular system that you are operating on P mu. And for if you will encounter the plane wave, of course this is also the exponential of I of a negative I k, or exponential of negative I scalar product of kx, and the momentum k mu is dotted to the x mu. So if you get the derivative of e to the negative ik dot x with respect to with respect to of course x mu, and then you will just get this. Sometimes you would also see this symbol h dot c dot. That's just means Hermitian conjugate. So if you see a matrix, that would just be the transpose times the complex conjugate, or that means the adjoint in general. For by the way, you will also be dealing with sigma. Quantum mechanics uses the Pauli sigma matrices. Also, this is also very common in quantum field theory. So we have sigma 1 associated with the x spin, and 2 for the y spin and the z spin, this sigma 3. So the relationship between the two sigma is represented by this one. You have a Kronecker delta ij that is just equal to 1 when I and j are equal, but 0 if they are not. And then the I here is just equal to square root of negative 1. The ijk here is running, the I, j, and k is running from 1, 2, 3. And then your k here would be whatever component that's on the third index here. So we also define sigma plus and sigma minus, where sigma plus is just sigma 1 plus I sigma 2, and the sigma minus is just sigma 1 minus I sigma 2 all over 2. So be careful with that. It comes out later on when we discuss the helicity and the spin of a particle. So now we will go to Fourier transforms and distributions. So we have here the Heaviside step function theta x, and this is just equal to 0 when the value of theta is less than 0, or the value of the argument here is less than 0. And this is just equal to 1 when the argument is greater than 0. Then we also have the Dirac delta function, which is just the derivative of the theta function here. And the integral of the Dirac delta function is equal to 1, of course. And of course it's ranging from negative infinity to positive infinity. By the way, if you have a Dirac delta function of n dimension, it should also be integrated in n dimensions to give equal to 1. By the way, the Dirac delta function is 0 except at x equals 0 for this particular delta function. But for x is equal to 0, the value of the Dirac delta function is infinity. So we also have the Fourier transform. So this expression, you are getting the Fourier transform, the integral of the plane waves in terms of momentum times the function here f tilde fk. That's just the inverse Fourier transform of f of x. So when you get the f tilde of k, this is just also the integral to the fourth of x e to the ik dot x f of x, which is also the Fourier transform of f tilde k. So it's just a matter of usage, the right usage. In three-dimensional transforms, the sign in the exponent will be positive and negative respectively. This is in the fourth dimension. So the integral of e to the ikx with respect to x to the fourth fourth dimension is just equal to 2 pi to the fourth delta to the fourth of k. By the way, you can review the definitions of direct delta functions in some books or in the internet. So, by the way, for electrodynamics, they use the Heaviside-Lorentz convention, where the Coulomb potential is given by this one, and alpha is of course this one here, 1/137. And the relativistic form of Maxwell's equation, if you've not encountered them before, are this one. This is the antisymmetric tensor, and where the F here is actually this one here defined, where the A are the four potential. That's the combination of the scalar potential and the vector potential here. So you can also review that. Now we go to the important thing in this particular chapter, the pair production in E plus E minus annihilation. So what's the most important thing to be learned here in quantum field theory is the quantum electrodynamics, because everything in quantum electrodynamics is completely studied. And so this is by far the most complete theory. But of course, as a basis of other theories, the quantum chromodynamics also is some of the concepts there are taken from QED, as well as of course the electroweak theory. The most completely worked out theory whose form is essentially determined by the relativistic invariance. So here, if you look at this figure is taken from the book of Peskin, where you have, and by the way, this lecture is also based on that book. So you have an electron, this one, coming into the right, and a positron going to the left. So they smash each other here and they produce a backscattering of muon and anti-muon. So this reaction is called the annihilation of E plus E minus to mu plus mu minus in the center of mass frame. And this means that P is equal to negative P prime. So most in particle physics experiments, they usually calculate the cross section, and they involve scattering of particles through collision of particles, or by shooting a target particle. So in this particular case, we consider E plus E minus just to make an introduction of this kind of experiment. So this is the annihilation of E plus and E minus, producing a pair of mu plus mu minus. So we start by firing a beam of electrons at a beam of positrons. So the measurable quantity in the cross section for the E plus E minus to mu plus mu minus as a function of the center of mass Cm, and the relative angle theta between the incoming electrons and the outgoing muon. So as you can see, it doesn't really mean that if you collide the electron and positron at this angle, it will produce a muon and anti-muon going also in the same direction, but they could be at an angle with the beam. So for simplicity, we work on the problem at the center of mass frame, where the p prime is equal to negative of, the p prime vector is equal to the negative p prime. The p prime momentum, the 3 momentum is equal to negative of p momentum. By the way, I'm sorry earlier that I wasn't able to put the vector sign above the p prime. This is supposed to be the correct one here. But the energy, of course, they're equal, so that they will just be at the center of mass. And of course here, the outgoing and momentums of the mu and anti-mu is also equal, negative of each other. So that's it. So assume that the beam energy here is much greater than either the mass of the electron or muon. But by the way, muon is much more massive than the electron. It's about 200 times more massive than the electron. So you can actually, if you have the ratio between electron and muon mass and you raise it square, you can just assign it to 0. So here is the momentum, this one, and this is of course equal to the half of the center of mass. And the electrons and muons have spin 1/2, and their orientations have to be specified when you completely solve that particular interaction. Also, we take the axis of the spin to be in the direction of its motion, so each particle can have its spin polarized parallel or anti-parallel to this axis. So you just use your right hand. So if your thumb is in the direction of the beam, then that's the parallel spin. And if your thumb with your fingers curling right thumb in the opposite direction of the beam, then it's anti-parallel spin. In practice, electron and positron beams are often unpolarized, and muon detectors are normally blind to the muon polarization as well. Hence, the cross-section must be average over electron and positron spin orientations, and sum the cross-section over muon spin orientation. So we will take a look at this later on, how these are calculated. but we will also be discussing about this here. So for any given set of spin orientation, it is conventional to write the differential cross section for this case, the mu1 produced into a solid angle, a mu1 produced into a solid angle d omega. So here you have d sigma, the cross section with respect to the solid angle, or the differential cross section with respect to the solid angle. This is just 1 over 64 pi square e square cm. This provides the correct dimension for a cross section. And then your m here square is the amplitude of a particular interaction, the square of the amplitude of a particular interaction, and this is dimensionless. So again, m is the quantum mechanical amplitude for the process to occur, and this star here is only valid for the center of mass scattering when the final state contains two massless particles. But then again, our products are quite massive compared to the colliding particles. Now, m is not known exactly. However, we can obtain it as a perturbation series in the strength of the electromagnetic interaction, where the first few terms in the series are evaluated. So this process will be dealt with later. We will do an example for this. So Feynman invented the Feynman diagrams to organize and visualize the perturbation series. So the most important Feynman diagram is a tree-level diagram, where the vertices are the least that you can see in a particular interaction, because sometimes the interaction involves can have many things going on between the initial and the final particles. So we usually consider the tree-level interaction. That means the Feynman diagram that has the fewest vertices. So in this case, you can see that it has only two vertices. This is a junction between at least three particles. So Feynman invented the Feynman diagrams to organize and visualize the perturbation series. And for a particular calculation that we are considering here, the lowest order term in the perturbation is this one. So you have E minus, or the electron, coming here, and then of course you have a positron also coming here. The arrow here is just telling you that it's in the inverse of time. So say we have our time direction here, so oh, I'm sorry, the time direction would be here, because you have the initial here and the final here, so, which is just the production of mu1s. So this is the time, and so your electron is coming with parallel with time, and positron is coming anti-parallel with time. And then this one here, you have an intermediate particle, the one that acts as a coupling to the vertices. It has a momentum q, where q here would be the sum of p plus p prime, and then, or this is also the sum of k plus k prime, the four momenta. And so this will be mu, and this would be mu plus anti-mu. So each external fermion must also have an associated spin state, because we don't know what the spin would be. But of course, later on we will average, because average with the, or they call it fermion spin sum. So each Feynman diagram can be translated directly into a contribution to M. The rules assign a short algebraic factor to each element of a diagram, and a product of these factors gives the value of the corresponding term in the perturbation series. So the perturbation series contains Feynman diagrams with increasing number of vertices. So recall, in QM perturbation theory, the transition amplitude can be computed for the first order as this one here. The HI there is the interaction part of the Hamiltonian. And in our case, we have the initial state E plus E minus, and the final state mu plus mu minus. We will learn how to use this notation in a while. So we can replace this one here with that, and this one with that. So the interaction Hamiltonian couples electrons to muons only through the electromagnetic field, but then not directly. They don't have a vertex that's for lines joining.